Today we're going to talk about how to determine target modes for a finite element model verification or validation or model updating study. Any real structure has an infinite number of modes to choose from, and even a finite element model might have hundreds of thousands or millions of modes that we could choose from. So we need some strategy to determine which modes do we care about. So there are several different methods that we could look at listed here. We'll go through each of these and talk about them in a little more detail. The first one basically boils down to take the lowest modes up to some frequency of interest. But we'll talk a little more about why that's the case. So remember that once we put a system into modal coordinates, we get a set of uncoupled equations for each mode, like this. The mode vector goes into the forcing, and then this is the force applied to the system. So this vector maps that force onto this modal equation. And in general, our force, in terms of amplitude versus frequency, might look something like this, right? Where there's going to be a low frequency region where the force is larger, and at some point the force typically loses strength. This is true for like wind loading, or on an airplane or something, or lots of different kinds of loadings tend to have a certain frequency range, and then they become small. So if we have some mode in the frequency range, it's going to be strongly excited and we need to account for its dynamics. But if we have modes out here, they're not really going to be directly excited. The only thing we might need to think about is this tail, or the static effect of these modes, right? Which can come into the frequency range of interest. But otherwise, our whole focus is right here on any modes that are in this frequency range of being dynamically active. If we need to account for residuals of these higher frequency modes, we've already learned how to do that using the mode acceleration method. So there's a little more that could be done. We could think about the shape of the excitation, or this inner product here, and what that might do to cause some modes to be active and others not. And of course there could be inputs that are band limited or have some other complicated form that might be a little more specialized. But this is the big picture at least. So basically, the most basic approach is to just take all of the modes in a certain frequency range of interest and count those as your target modes. There are other things we might think about as well. Just because a mode is strongly excited doesn't mean that it's more important than others. Some modes might put higher stresses in for the same level of excitation or level of displacement. So this plot shows the different fixed interface modes of a clamped beam. So clamped on both ends. And they're all normalized to have about the same amplitude, you can see here. If we were to calculate the stresses from these modes, this highest order purple mode here would have much higher stresses than mode 1 if this was the true displacement. Because it has higher curvature, and curvature relates to the moment, and so these things have to be taken into account. Typically, though, what happens is that as the frequency goes up and a mode becomes more complex, its stiffness goes up. So if the force is limited, and if the force is constant for all the modes, then we tend to see that the low modes have the largest excitation because they have the lowest stiffness, and they end up being the ones that contribute most to the stress, even though the high frequency modes would have incredibly high stresses if you could drive them to the same amplitude. And this can all get much more complicated. Imagine you have a rocket with feed lines and pipes and bolted joints and engines and all these different parts, right? There might be certain components that are much more stress sensitive than others. And so again, in a detailed problem, this could get much more complicated. Another thing we have to think about is what if we're not interested in an entire vehicle? Everything I said so far kind of assumes that our whole structure of interest is this whole is considered all at once, or we're kind of implicitly assuming that these are the modes of the fully assembled rocket. But sometimes we need to select target modes just on one subcomponent, just on one piece. And so how can we relate those to the motion of the assembly, and how do we know how many target modes to take in that case? Here, everything that we've covered in substructuring is really handy. If you recall on homework 4, we were assembling two beams together, two cantilever beams at their free end here. And we found that using two constraint modes in each and a few fixed interface modes in each, we were able to accurately estimate the first 6 modes of the assembled system. Right? So using this, we know that a highly accurate model for this system is just one that includes these ingredients, and we don't need any more. So if we have a model that can accurately predict all of these modes, then we will accurately predict the first 6 modes of the assembly, or all the modes of the assembly up to a frequency range of interest. So using that concept, we can go back to any structure and we can come up with rules for how many fixed interface modes we might need to capture for each subcomponent to make sure that when we put all of those together, we have an accurate model for the full assembly. It's important to note that one of the really important ingredients was these constraint modes. We saw in the homework that if we didn't include the constraint modes, if we just used free modes, the accuracy was far less. So these are important, and these are static effects, and they have to do with the boundary degree of freedom and stiffnesses near the boundary degrees of freedom. So putting all this together, we could start to come up with a test plan, right? Maybe some static testing that exercises the interfaces and allows us to understand what's happening with these modes, and some dynamic testing to estimate the dynamic modes. So this is one concept. Another thing to remember is that if we talk about a vehicle as a whole, so if we're talking about the entire launch vehicle, well, there might be many different configurations we need to worry about. For example, with Space Shuttle, there was the on-the-pad configuration. There was right after you break free of the pad and you cut the connections to the vehicle, there's another configuration. And then you have a configuration where the booster rockets are gone, and then one where the orbiter is by itself. And so you have all of these different configurations, and that's not to mention the fact that the fuel half full, third full, 3/4 full, all of those are different cases because the dynamics are different. So when tackling systems like this, a lot of what we're going to say about selecting target modes is only really qualitatively applicable. In these types of cases, you can say a general rule is you just want to have enough target modes that you can stress the FEM in enough different ways that you can hopefully guarantee that your FEM has the right mass and stiffness distribution and doesn't have any errors, any things connected that shouldn't be, or other problems. So here are just some mode shape animations so you can kind of picture that, right? If we took the first 3 modes of my grossly simplified model of the SLS, we can kind of see what each one is stressing. This stress is like the core of the vehicle. Here we're mostly probably getting high stress in these joints between the boosters and the core. And here as well, that maybe we're also getting bending in the boosters in these. And if we kept going on up, we could see all the different ways that the vehicle deforms, and hopefully eventually gain enough confidence that there weren't any glaring errors in our finite element model. Another class of problem has to do with small components, and components that might be attached at a boundary somewhere. So if we go back to the SLS, imagine some examples of small components could be the engines at the bottom of the rocket. They're kind of going for a ride as the whole rocket is moving and shaking, and they're basically just along for the ride. Or lots of or a little tiny electronics box that's bolted into one of these parts, or any of those things could be a subcomponent that we're interested in. And often these things are even tested in a lab, where they might be mounted on a large electromagnetic shaker like this, and we might shake the base up and down as our component rides on top and see what happens to that component. So we can actually use the Hurdy-Craig-Bampton formalism to directly derive which modes matter in a base excited case like this. And it's really useful and leads to one of the important metrics of effective mass. So to derive that, consider we have a Hurdy-Craig-Bampton model that has a couple fixed interface modes, a certain number of fixed interface modes, and then it also has a certain number of constraint modes, psi. And this is a case where we have one boundary degree of freedom, so the constraint mode is actually similar to a rigid body mode. We're going to exploit that later. But so to create a Hurdy-Craig-Bampton model, you remember that we would partition our mass and stiffness matrices to O-set or interior or discarded degrees of freedom, and to A-set or boundary degrees of freedom. And then we'd solve an eigenvalue problem on the O-set to get the fixed interface modes. And then we are able to construct the Hurdy-Craig-Bampton transformation between fixed interface modes and their amplitudes, and the boundary motion, the motion of the A-set, and these constraint modes. So once we have that transformation, we use that to relate the original coordinates to this reduced set. And to accomplish that, we plug in, and our reduced mass matrix becomes THCB transpose times the mass matrix times THCB, and we'd have the same thing for the stiffness matrix. So I won't go through all the details, but as you do that multiplication, we get a term here that has the mode shapes, the fixed interface modes transposed, the mass matrix on the O set, or the set we're discarding, multiplied by the constraint modes on the as well. And then we also have an off-diagonal term in the mass matrix. So if we go through this, this would be symmetric down here, so we'd have that same term transposed down here. And the A set just becomes the Gaussian or static reduction down to the interface degrees of freedom. So we've seen both of those when we talked about static reduction. All right, so what happens if we take the equation of motion, so this matrix times the coordinate vector here, and we multiply through. The identity gives us just an identity times q double dot. This term ends up coming in as well. It's multiplying the acceleration at the A set, and then everything else will be 0 except for this term here, which has the fixed interface mode amplitude and their eigenvalues, their natural frequencies. So that's the top equation. Let's just talk about that one for a minute. So this equation only involves those three things. And if we move the boundary motion to the right-hand side, now suddenly we see this is the fixed interface system in modal coordinates, so each mode of the fixed interface system one at a time. And on the right-hand side, we have this term, which is a forcing term. It acts to translate the motion of the base and turn that into a force and tell us how each of the fixed interface modes will be excited if we shake the boundary. Does that make sense? So imagine our picture up here again. If we took this structure now and we grabbed it at the clamped end and we shake up and down, this is now telling us how much will each of these different fixed interface modes get excited by that motion of the boundary. And it happens through inertial coupling. It's the you can think of it, another way to think of it is if we change reference frame, rather than moving the boundary, we can say the boundary is fixed and we're applying an acceleration, a distributed acceleration across all of the nodes here in the structure. And if we're talking about this rigid body motion, we could also have a rotation at the boundary and other things. But you can think of that as a distributed inertial load. So either way, this term is really important because it tells us how the boundary motion causes the fixed interface modes to be excited. We also have a second row down here that we can think about. So if we take that and we want to plot that, that row, the first term is the transpose of the term that we were just looking at here, and that multiplies the fixed interface accelerations, and then we get two other terms, and then finally we have the forcing. So the forcing, the force at the boundary, this is what we might call F sub B. So what this shows us then is that this term, this off-diagonal mass matrix term, is the connection between the acceleration of the fixed interface modes and the forces that that produces on the boundary. So it relates those accelerations, or the modal or the dynamic motion, to the forces at the boundary. So this is an important term. It's sometimes called the modal participation factor, but I've seen that name used for other things. I don't know that that's universal. But anyway, we'll call that matrix P, and it's given by this product between, again, remember these are the fixed interface modes, and these are the constraint modes of the system. Okay, so we have these two equations, and that both involve P, and I left out the boundary motion in this second one. So they're important in these two different ways: how the fixed interface modes get excited, and how those modes transfer forces to the boundary if they do get excited. So we use that to construct metric. Often what's done is to do the piecewise square, to square each term. That matrix will have a size of number of modes by number of interface degrees of freedom. So we can take the piecewise square to add them all up, and then typically normalize. There are a few different ways to normalize. One way is to use the trace of the matrix M, which is just P transpose P. So I'll have a size number of sensors by number of sensors. And then you add all that up. Basically, that's the total mass. Number of sensors, I guess I should say number of boundary degrees of freedom, or number of types of interface motion. So this could work for a system, any system, and Kammer and Triller presented this in the 90s. What's most often done is to limit this to the special case where we have just enough boundary degrees of freedom to eliminate all of the rigid body motion. And the important thing here is that the rigid body modes will then be equal to the constraint modes. And just as we saw in our simple example up above. And in that case, we can derive a metric, and this metric above, except for maybe a different normalization strategy, but that metric above becomes identical to what's commonly known as effective mass. So this justifies the use of effective mass as a metric to determine which modes are important. And the important thing to remember is that this is all based on having a fixed boundary somewhere and looking at basically fixed interface modes relative to that boundary in a Hurdy-Craig-Bampton type formalism. So what's typically done is to compute this effective mass factor for each of the modes, and then figure out how many modes do we need to have 90% of the effective mass of the whole structure captured. And so that's the typical approach. I can show you an example here. This is just a review of what we just saw, but say we have a cantilever beam where we have a fixed boundary and a free boundary. This is what one of the flexible modes would look like, the first mode. These are the two rigid body modes that we would have, or the two constraint modes if we have the only a set degree of freedom being on this boundary, the displacement and rotation. And so those are the ingredients. We plug those into the formula. Oops. Okay, sorry. We plug those into the formula, and we can finally compute the modal effective mass. So for each rigid body mode, or each direction of motion of the interface, we have a different value for, we have a value for each, we have a total mass, so these columns should sum to 1. And then these numbers tell us the fraction of contribution of each of the modes to the column. So for translation in the y direction, we see that the first mode has 73%, captures 73% of the mass of that mode. So again, if we were to shake the boundary in the y direction, if we have a model with only mode 1, we'll capture 73% of the force that goes into the boundary in the y direction due to this motion. Similarly for rotation in z, notice the first mode captures 97% of the rotation of the structure. And we need to add the second mode to get the total to near 89%, and then the rest of the modes start to capture much, much less. So just using the first 3 modes in this example, we capture 90% of the rigid body mass in both of these directions. So, and the same is seen in lots of different structures. And so this is a common metric that you'll hear about, and this is a way that you can compute which modes matter. And again, it's mostly kind of geared towards a small component that you imagine is riding somewhere, is bolted onto something and is riding somewhere. And you're interested in how it will be excited by that trip. But it can also be part of a substructuring model where we think of these as ingredients for each part of an assembly, and looking at the loads that each of those will see.